This lecture is going to talk about the concepts of heat and work. Now, both of these words, heat and work, are very commonly used every day, but in thermodynamics they have a very specific meaning, and we need to make sure that we understand what that is. So we'll begin with heat. So when a system is not in thermal equilibrium with its surroundings, heat can flow across the system boundary. So remember, the property that defines whether a system is in thermal equilibrium or not is the temperature. So this is essentially saying if there's a temperature difference between the system and its surroundings, heat can flow across the boundary. Notice it says can, not will, because if the system is insulated from its surroundings, of course, that will prevent heat transfer from happening. A key thing here is that there needs to be a temperature difference between the system and the surroundings in order for there to be heat transfer. Now, very important to realize that heat is a means of energy transfer. It is not energy. So heat and energy are two different things. Heat only has meaning in the context of transfer across a system boundary. So the driving potential of that transfer must be a temperature difference. If there's no temperature difference, there is no heat transfer. Heat is not accompanied by mass transfer. So this means if we have a hot cup of coffee and we want to cool it down by putting a little bit of cold water in it, that's mass transfer. So the temperature of it will certainly go down, but it's not heat transfer that's doing it, it's mass transfer. So heat is not accompanied by mass transfer. We're certainly going to be looking at situations later in the course where there is mass transfer, and we will learn how to account for that, but that's not called heat transfer. Heat is not a property of state, and this is a very important thing to remember. Remember, in the last lecture we listed a whole bunch of properties: pressure, temperature, volume, specific volume, energy, internal energy, a whole list of the properties of a system. Notice that heat was not in that list because it's not a property of state. And I'm going to try to illustrate the difference between a property of state and a quantity such as heat here as we go forward. The amount of heat transfer depends upon the path of a process. This is a really important thing to remember. Depends on the path of the process. In other words, it depends how we got from one state to another, how much heat is going to transfer. The sign convention for heat transfer, and this makes sense in the context of our defining a system and its surroundings, heat is positive when it's transferred into the system. So when we add heat to a system from the surroundings, that is considered positive heat transfer. And we need to learn that sign convention to get the signs in our energy balance equations that will come later on to get that all right. Let's just take a look at a little example here. Let's say that we have a system in a particular state, state 1. And then heat transfer happens during this process to state 2. You'll notice that a volume change is also happening because the piston has been pushed down. But heat transfers during this process. So we go from 1 to 2 with some heat transfer. Well, when we look at this on a property diagram, and the property diagram we're going to use is going to plot pressure versus volume, certainly we can see that the volume is decreasing, so we're going to be moving in that direction on the PV diagram. But of course the pressure is also going to change. So in this illustration we'll say we're going from point 1 to point 2. So those are both states because they describe the condition of this system at point 1 and the condition of this system at point 2. So we're moving between two different states. Well, there are a lot of different ways to get between those two states, and this shows two possible paths between state 1 and state 2, path A and path B. Let delta Q be an infinitesimal amount of heat transfer. In other words, as we move perhaps from there to there, a very, very short distance across that path, there'll be a tiny little bit of heat transfer, and that is called delta Q. Well, if we add up all of the delta Q's that happen along path A, and that's all integration is adding, so we go from state 1 to state 2, adding up all the heat transfer that occurs as we go from state 1 to state 2, that is not going to be equal to the amount of heat transfer that happens as we go along the second path. So the amount of heat transfer depends upon the path. Different path, different amount of heat transfer, even though we're starting and ending in the same place. So this is an extremely important characteristic of heat transfer that we need to remember. Notice when we're talking about heat transfer, saying that the integral from 1 to 2 of delta Q is equal to Q2 minus Q1 doesn't make any sense, because Q2 and Q1 have no meaning because they're not state variables. We don't say that the amount of heat at state 1 is a certain number of kilojoules and the amount of heat at state 2 is a certain number of kilojoules, and we just subtract the two to find the difference. That's not what this means. So instead, we use a different notation. We say that the amount of heat transfer going from 1 to 2 is equal to 1 Q2. So this denotes the amount of heat transfer during the process from 1 to 2. This doesn't have any meaning. Now, for properties, remember, heat transfer Q is not a property. But if we were talking about a property, and for example, we'll talk about temperature here, then the integral from 1 to 2 of dt, which just means we go from 1 to 2 and we add up all the small temperature changes that occur as we go, then that is equal to T2 minus T1. So notice for properties, this is true, that the temperature difference between 2 points is just simply the difference in the temperature at those 2 points. So the integral from 1 to 2 of dt is T2 minus T1, but only for properties, not for so-called path functions like heat transfer. So a property can be assigned a value without knowledge of the history of the system. So we can tell you what the temperature of the air in this room is without knowing the history of the system, without figuring out how much heat was added or what the temperature used to be. We can just measure the temperature and state what it is. So a property can be assigned without knowledge of the history of the system. Now I want to look at an analogy in order to help explain this difference between a path function and a state function. Let's forget about temperature and heat transfer for a while. Let's say we're just talking about motion on a plane. So a flat plane and we're just moving around on that plane. So we denote our position on the plane by our x and y coordinates. So we have those two coordinates that tell us where we are on this plane. And notice I've got 2 points on the plane identified here, point 1 and point 2. So that's fine. You can think of those as 2 states, and the 2 properties that we're looking at here are the x and y coordinates. So this is sort of like a property diagram. Well, if we take a look at a state function, and an example of a state function in this context would be position. So let's pick the x coordinate. Well, if we integrate from 1 to 2 and we add up all of our changes in x as we go from state 1 to state 2, or from position 1 to position 2, then the result is just x2 minus x1. So this is an example in the context of motion on a plane of a state function. Just position x is a state function. Y, of course, would also be a state function. Now let's take a look at a couple of different ways to get from point 1 to point 2. In other words, a couple of different paths from point 1 to point 2. So we could move from point 1 to point 2 along this path, which I've called path A, or we could move along path B to get from point 1 to point 2. And of course, there's an infinite number of ways to do that. Well, notice that if we move along path A and we add up all the tiny little changes in x, which we call dx, we're going to get exactly the same answer as if we move along path B and do the same thing. And that answer will just be the x coordinate of point 2 minus the x coordinate of point 1. So this state function, the change in this state function, is independent of the path that we move along. So that's why it's called a state function. And thermodynamic properties like pressure, temperature, volume have that same characteristic. On the other hand, if we look at a path function in the context of motion on a plane, an example of a path function would be the distance we traveled. So delta L is a small segment of one of these paths. So if we integrate from 1 to 2 along path A, adding up all the delta L's, we get the distance that we've traveled. Well, we would never say that that's equal to L2 minus L1. L2 and L1 really don't make any sense. What is the length of the path at point 1? What is the length of the path at point 2? That doesn't make any sense. The length of the path only makes sense when you designate what path you're going along as you go from 1 to 2. So the distance traveled here is a path function, not a state function, because its value depends on the path you follow as you go from point 1 to point 2. So position x is like a state property, pressure, temperature, etc., whereas distance traveled is a path function. So that is similar to heat transfer. Or heat transfer has that same characteristic. It depends on the path you take. Now we want to move on and look at work. And work has many of the same characteristics as heat. So the thermodynamic definition of work is that work is done by a system on its surroundings if the sole effect on the surroundings could have been the raising of a weight. So notice here that is talking directly about a force acting through a distance. In order to raise a weight in the surroundings, you need to exert a force through a distance. And force acting through a distance is the fundamental definition of mechanical work. So if there's energy crossing a system boundary, and it is not due to a temperature difference, then it is work. So by definition, what we're doing here is saying there are only two ways that energy can transfer across a system boundary. That is heat transfer, and that happens if the energy transfer is due to a temperature difference. And then there's everything else, and that everything else is called work. Now, work also is not a property. When we look at a system sitting at a particular state, we would say it has a temperature of 20 degrees. It has a pressure of 1 megapascal. But we would never say it has a work of 30 kilojoules or something like that. It just doesn't make any sense. Work is not a property of a system. It is a characteristic of a process where the system moves from one state to another. So it is also a path function, and we would use this, or we will use this same type of notation. The integral from 1 to 2 of delta W is equal to 1 W2. So this is the work as we go from state 1 to state 2. So for the types of systems that we're going to look at, the mode of work transfer across a system boundary is going to be restricted to mechanical work. And as I said, that's the product of a force and a displacement. So we have here a picture of a block of material sitting on a floor, and we're exerting a force on it and pushing that material to the right. So when a force acts through a distance, we get a work transfer. And here the distance is denoted by this coordinate x. So work is defined as the integral of force times dx. Now if the force happens to be constant, then of course this is just the force times the distance it is moved, but the more general case has to allow for that force changing for whatever reason. So the work is the integral of f dx. Well, it turns out that in the context of thermodynamics problems that we're going to look at, force and displacement aren't very convenient variables to work in. So we want to relate force and displacement to properties that are more common in a thermodynamic setting. So the more likely force that we're talking about here is the force that we need to exert on a connecting rod in order to make a piston move and change the volume of a system. So rather than talk about force and displacement, we would prefer to evaluate work in terms of pressure and volume. Well, there is certainly a connection between these properties that allows us to write this equation in terms of these properties. So that's what we're going to look at here. So the force that we need to exert on this piston is equal to the pressure of this substance times the area of this piston face. So the force is equal to the pressure times the area. Now also, the displacement of the piston, so as it moves a small distance dx, that's going to result in a change in volume, and that dx, that distance, is going to be the change in volume divided by the area. Another way to think of that is that this volume is equal to the displacement dx times the area. So there's a connection between the force and the displacement and the pressure and volume. So we're just going to take the force and replace it with PA, and we're going to take the displacement dx and replace it with dv over a. And when we do that, we get work is equal to the integral of PA dv, but then of course these a's cancel, and we get work is equal to the integral of P dv. This is a basic equation that we're going to be using over and over again to calculate the work transfer for closed systems like this. Notice this is a closed system. So the closed system work transfer, written in terms of variables that are convenient for studying thermodynamic systems, is work is equal to the integral of P dv. Now this will also highlight why at the beginning of the course here a PV diagram is so useful. So if we look at a process on a PV diagram, so here we're going through an expansion from point 1 to point 2, and we've shown the path on a PV diagram. Notice that work equals integral of PdV tells us that work is the area underneath this curve. So this is the reason why a PV diagram is so useful for looking at closed system problems, because if we know what that path looks like, we can calculate the area underneath it, and that's our work transfer. So this also highlights the fact that work is a path function, right? Remember we said that it's not a state function, it's a path function. Well, certainly the area underneath that path depends on what the path looks like. If we go from 1 to 2 along this path, then that's the area. But if we happen to go from 1 to 2 along this path, then of course the area would be larger, and therefore the work would be larger. So this helps us to remember that work is a path function. It's the area under the curve, so the shape of that curve, exactly where it goes, is important in figuring out the work. Now there are other forms of work, in other words, other forms of energy transfer across a system boundary that we're not going to look at in this course. We're going to restrict ourselves to the mechanical work that we've just been talking about, but an example of another one would be electrical work. So this red dotted line is our system boundary, and we have an energy transfer across that system boundary, but it's not due to a force acting through a distance. Instead, it's due to a current flow acting as a result of a potential difference. So the rate of work transfer here would be the potential difference times the current. So there are other modes of energy transfer or other modes of work transfer, but we're not going to look at those in this class. Now, what is our sign convention for work? Work is considered positive when it is done by the system. So if we have a system doing work on the surroundings, that is positive work. And if we just go ahead and evaluate the integral, work equals integral P dV, as long as we set that up properly, it will give the correct sign for the work. We don't need to calculate the magnitude of the work according to that equation and then just throw a sign on after we're done to make it right. the equation will give us the correct sign if we treat it properly. Next thing I want to talk about is quasi-equilibrium processes, because this is a very important part of understanding the equation that we're going to use, work equals integral of P dV. So what is a quasi-equilibrium process? This little illustration helps us to understand quasi-equilibrium processes. So we have a gas of some sort here that is undergoing an expansion. And the way that this expansion is occurring is the piston is loaded up. In other words, this gas is pressurized by a whole bunch of tiny little masses sitting on top of the piston. Well, if we were to remove these masses one at a time, then what would happen is we'd reach in here, we'd grab one of these masses and take it off, and of course the piston would raise up a tiny little bit, and the gas in here would be disturbed, and it would move around a little bit for a few seconds, and then it would settle out again. Well, if we're removing very small masses, then this gas will be very close to equilibrium at all times during this expansion, and that is what a quasi-equilibrium process means. So as each mass is removed, this system is momentarily disturbed from equilibrium. However, a new equilibrium will be very quickly established, and if these masses are very small, infinitesimally small, then we have a quasi-equilibrium process. So if we were to draw this process on a property diagram, and again it doesn't really matter what the axes are, all of the states that system passes through would be equilibrium states. And by equilibrium states we mean that all parts of the gas are at the same pressure. There's not high pressure regions in one part of the cylinder and lower pressure regions in another part. It's all at equilibrium. Same could be said about the temperature or the specific volume or any other property. All of the properties inside of that container are the same everywhere. So it's in equilibrium. There are not pressure gradients, temperature gradients, or any other type of gradient inside of the system. It's at equilibrium. Well, it turns out that that is one of the conditions under which this equation is true. So anytime we use this equation, we need to remember that we're assuming this process is quasi-equilibrium. In other words, very close to equilibrium, not just at the ends, but at all intermediate states that form the path as we go from one point to another. Now the reason for that is, notice we're using just a single value for the pressure here to represent the force that's being exerted on that moving piston boundary. So if we go back to our little sketch here, the pressure P inside of this system is assumed to act everywhere on this piston face equally, so that we just have a single value of pressure acting over this piston face A, and that's what gives rise to the force. And remember, that's why we came up with this equation. Well, that's only true if the pressure everywhere in this system is one uniform value. So this gas has to be in equilibrium for this equation to be useful. So every time we use this equation, we'll be making the assumption quasi-equilibrium process to go along with it. So for a quasi-equilibrium process, this is the pressure of the entire volume. That P in there is the pressure of the entire volume. Now what I want to do is take a look at a few specific types of processes and start to learn how we would calculate the work transfer for these different processes. So there's a few of them that we'll look at here. The first one is an isometric or isochoric process, and that is a constant volume process. So if we look at this on a PV diagram, a constant volume process is going to be a vertical line because this axis is volume. So a constant volume process will look like this on a PV diagram. Now remember that the way that we calculate work is as the integral of P dV. So the work as we go from point 1 to point 2 is 1W2, that's the integral PdV. And remember also that that is just the area underneath the line, and of course a vertical line, the area underneath it is 0. So the work for a constant volume process for a closed system is 0. So if there is no change in volume, there is no work because there is no displacement. So this is kind of the same as if you were to walk up to a wall and push on the wall. You push on it all day long, you've exerted lots of force, but if there has been no displacement, then you have done no work, because you need both force and displacement to get work. Well, in the thermodynamic context, if there's no volume change, there is no work. So a constant volume process, the work calculation is very simple. It is by definition 0. The next process we're going to look at is called an isobaric process. This is a constant pressure process. So because pressure is the vertical axis on our PV diagram, this is a horizontal line. So here's an example going from a low volume to a high volume with a constant pressure process, horizontal line. Well, our starting point for calculating work is still the same. The work from 1 to 2 is the integral from 1 to 2 of PdV. That's always our starting point for calculating work. In this case, though, the pressure is constant, so pressure can come outside of the integral sign because it's constant. Then the integral from 1 to 2 of dV is just V2 minus V1. So the work calculation for a constant volume process is P times V2 minus V1. And remember, of course, that the work is the area underneath the PV diagram, so that is just this area. P being the height of this rectangle, and the change in volume being the width of the rectangle. So work is integral to PdV, which is P times V2 minus V1 for a constant pressure process. The next process we want to look at is an isothermal process. And isothermal means constant temperature. Now here we have a problem. For the previous two, isochoric and isobaric, one of the two axes on our PV diagram was constant, so we could just draw either a horizontal or a vertical line. Here though, temperature is not one of the axes on our PV diagram, so it's not quite that simple. In fact, now it depends what type of substance we're looking at. So an isothermal process follows along a line of constant temperature, but we need to know, what does a line of constant temperature look like on a PV diagram? Well, that depends on the substance, and we're going to be learning a lot about that as we move forward, so it's a little bit too soon to be drawing isothermal processes. So here's an example of what a line of constant temperature looks like when we have a substance that is changing phase. We're going to be talking a lot about this diagram in the next section of the course, but here this substance is a liquid, here it's a liquid vapor mixture, and out here it's a vapor. So certainly as we move along this line, the integral of PdV is still the area underneath that line, but obviously it depends a lot on where we're starting and ending on how exactly we would go about calculating that. The last process I want to talk about in this section is a polytropic process. Now a polytropic process is described by PV to the n being a constant, where this n here, which is an exponent on the v, is called the polytropic index. So notice that the two properties involved in this expression are pressure and volume. So we can look at a PV diagram and see what this might look like. Well, this is an inverse relationship between P and V, meaning that as one of these increases, if their product is going to remain constant, the other one has to decrease. And that's true of polytropic processes. As one goes up, the other has to go down. Now, just exactly how fast they go up and down is governed by this polytropic index, n. So we'll take a look at several polytropic processes on the PV diagram. If we happen to let n equals 0, Well, v to the 0 is just 1, so p is equal to a constant. So a polytropic process with n equals 0 is actually just a constant pressure process. So that's one of the limits of the different values that n might take. So n equals 0 is an isobaric or a constant pressure process. The other extreme, if we let n be infinity and we plot this, we actually get a vertical line. So n equals infinity is an isometric process, or a vertical line on a PV diagram, and we've looked at how to calculate work for those two cases. But a polytropic process can have any value of n between 0 and infinity. So if we look at some intermediate value, then that path is going to look like this. So again, this is an inverse relationship. As the volume increases, the pressure decreases. As the volume decreases, the pressure increases. Now exactly how steep this line is governed by this value of n. A very, very large value of n, and we'll get a very steep line here. A very small value of n, and we get quite a shallow line here. So a polytropic process is an inverse relationship between P and V. Now we want to take a look at the work for a polytropic process. So PV to the n is equal to a constant, describes that path on the PV diagram. So I'm just going to call this constant capital K just to make it a little more compact to write. We calculate the work for any process as the integral from 1 to 2 of p dv. So what we want to do is take this description of the path and substitute it into our work equation to calculate the work for a polytropic process. So to do that, we let the pressure in this equation be equal to K divided by V to the n. In other words, KV to the minus n. So P dV is the same as kV to the minus n dV. The k, of course, is a constant, so it can come outside of the integral sign. And then we just evaluate v to the minus n by adding 1 to the exponent, so that becomes 1 minus n, and then dividing by that new exponent, so 1 minus n in the denominator as well. And because we're integrating from 1 to 2, we evaluate this expression from 1 to 2. So this is the same expression again on the next line here, but what we can do is get rid of this constant here and replace it with PV to the n. So that's just taking our original equation, constant equals PV to the n, and substituting it back in here to get rid of that unknown constant K. Now if we take a look at this, V to the n multiplied by V to the 1 minus n is just V. Remember, you're multiplying these together, so you add the exponents. N plus 1 minus n is just 1. So this is actually PV over 1 minus n, and it's evaluated from 1 to 2. So the last thing we do is substitute in those limits. So the work from 1 to 2 for a polytropic process is P2V2 minus P1V1 over 1 minus n. So this will be an important equation that we'll use quite a bit to calculate the work for a polytropic process. Now notice that there's a problem with this equation for one particular value of n, and that is for a value of n equals 1. If n is equal to 1, this equation doesn't work. So let's just take a look at what happens to this equation when n equals 1. Well, we can certainly see an issue in the denominator here. 1 minus 1 is going to be 0. So we might say, well, gee, this work is going to be infinity because we got a 0 in the denominator. However, that's not quite that simple, because if we look at the numerator, we look back up to this equation, if n is equal to 1, it means that P2V2 equals P1V1. So the numerator is 0 and the denominator is 0. So this is an indeterminate expression. We can't tell what the answer is going to be. Now, we can overcome that problem by rewinding and going back to this stage and doing this development over again for the specific case of n equals 1. So that's what we're going to do next. So for n is equal to 1, PV is equal to K. And so The work expression starting at the same point is just K dV divided by V. So we've just rearranged this equation and said P is equal to K over V, and then substituted it in there. And of course the answer to this is K log V, evaluated from 1 to 2. And so that's K log V2 divided by V1. And again, we can replace that constant K with P1 V1. If we wanted, I guess, we could also replace that constant K with P2 V2. So this would be an equivalent expression. Which one of these we use probably just depends on whether we know more at point 1 or point 2. But this is the work for a polytropic process with a polytropic index of 1. P1 V1 times the log of V2 over V1. But all of these expressions for work all come from this starting point. Work is equal integral of PdV, and then we put our knowledge of the particular path we're following in there and come up with the expression for work for that particular path.